Today I'm here at IGW where they turn massive aluminium blocks like this into this complex machine part. Whether it's precision medical equipment or the state-of-the-art in lithography machines at companies like ASML, the future demands really big, very precise milled metal parts.
We can all imagine small parts being precise. For instance, in a mechanical watch, we assume tolerances of just a few microns. But as technology advanced in other fields, we need to adhere to tighter tolerances on big parts as well. Take, for instance, the medical imaging sector, where we depend on a live radiology feed for heart surgery. We need to be able to move the camera very precisely and not lose track of where we are. As soon as the size of these parts increases, the complexity in production rises as well. That's where years of experience comes in handy.
And that's why I'm here at the IGW production facility in Oostkamp, Flanders, Belgium.
Yep, in Flanders Fields lays this 20,000 square meter workshop where knowledge meets metal.
I'm here on the factory floor today, joined by Jorne. So first off, I just wanted to get clear, like you guys are known for industrial gears.
Yes.
But for a long time now, you guys have been specializing or advancing that know-how in machining parts with very high precision.
That's correct. One of our customers came with a problem and wants to have a solution where we had some conventional milling machines. And we started with some first products, very prototyping for them. And now, as we speak, we are still having those customers in our portfolio. And those machines, those products, are very sophisticated nowadays. And we grew together, technology-wise, but also product-wise and also capacity-wise in our factory.
I can imagine, because today it's more automated. It's obviously all, as opposed to 40 years ago, computer-based, CAD-based. So let's go to the very beginning of the production process. Let's have a look. So what's happening right here, right now?
So at the moment, our product engineer is simulating with the simulation software the milling paths. This is before the part is really going on the machine in order to not cause downtime at the machine. So simulation-wise, we can simulate if the milling paths are correct, that there is no collision up front. That is then going to the machine once it is validated. And then the programming is really in execution mode. And the operator, together with the product engineer, is doing the first prototype.
Once engineering has validated the full process in simulation, it's time to move to the shop floor and start working with real material.
All right, so back on the production floor.
Yes, so when the engineering has finished their first task, I would say, developing how the part should go to the shop floor, we are getting raw material, like for example here a sand-casted C-arc in aluminum.
All right.
Whereas we are putting that on the machine, which we are going to see later on the fixtures. But next to this sand-casted aluminum, we also have, for example, here a solid block of aluminum, which is arriving from the supplier, just in a rough state.
Cool.
We have various kinds of material, aluminum, cast iron, steel, in various kind of shapes, depending on the application, depending on the customer, and even in the portfolio of the customer, we do have different kind of parts.
Just to get an idea, like MOQ, what are we looking at? How many parts do you guys produce for these type of clients?
We do have more, I would say, a flexible oriented production system. So a typical MOQ of a batch we don't require. For the different kind of customers, we do have sometimes volumes of 500, 200 a year, but in some cases even a few thousand.
Yeah. Your clients include, medical supplies, they include the lithography, the semiconductor industry. What are other examples of parts that need this level of precision?
Well, I would say everything which is operating in a high demanding industry, where there are components required, all require these kind of tolerances and require these kind of dimensional challenges.
The requirements don't get more precise than this.
No, because if you look to the tolerances that are required on a certain distance, in combination or in relation with each other, those parts are quite challenging.
Lithography machines themselves operate at insane levels of precision, producing semiconductors at near atomic scale. That's down to 3 nanometers, only limited by the thickness of the light waves themselves. As you can imagine, all the equipment inside these magic boxes needs to be mounted with ridiculous precision. The part we're talking about has some surface tolerances of 30 microns. That's about half the thickness of an average human hair. To make these parts, IGW relies on some truly jaw-dropping equipment.
You guys are investing in new machines all the time, trying to redefine the pace of this industry. What is the crown jewel?
Well, I would say our latest investment, which is our Starrag machine, where we do have the ability to produce our parts, I would say, in the next generation in terms of production. We do have developed dedicated tools and fixturing, like hydraulic clamping, in order to even go the next mile with regards to production efficiency, but also zero defect mentality. All these kind of parameters are incorporated in these kind of new technologies. And over the past years, we kept investing in different kind of machines in order to keep this pace on this rapid changing industry.
To tell me more about this massive installation, I'm accompanied by Luk. He oversees production together with a team of highly skilled machine operators.
Now we're going to the control hub of the machine.
This control unit over here, yeah, he can monitor all the process parameters, follow the continuation of the production process per part.
So what are like the main difficult things with machining a large, very precise part like this? Is it the temperature control or?
That's one of the difficulties to tackle. That's temperature.
On small parts, the expansion of metal can almost be neglected. But if you're milling a part of almost 2 meters in size and expect it to be accurate down to a couple of microns, an increase of just a few degrees will offset the size of the part too much. So the Starrag at IGW measures the surface temperature of the part and the tool head to automatically compensate for the expansion rate of the specific material.
This machine has a huge footprint. Can you take me through what it takes from beginning to the end to mill a piece on this machine?
The first step in the process, so after the part has gone inside the machining area, is determination of the volume. The machine itself doesn't have eyes, let's say. It cannot see like we humans can do and then relate to where exactly is that part positioned at this moment. So this is probing, a highly accurate measuring system that is implemented into the machine and system.
Using a probe, the machine senses where the rough sand cast part is positioned in 3D space. As soon as that's done, it can adjust its predefined milling paths to the orientation of the rough part.
So it measures where the part is, and then, according to those measurements, starts with the first slice of milling, I would say.
The tool magazine has a capacity of 220 tools. Wow. So we have 220 pockets, meaning if the tools have a maximum dimension and diameter of maximum 100, meaning that we can load 220 tools.
Right. Wow. When this is running on a 24/7 basis almost, how often do these tools need replacing or maintenance?
So a tool life is either a calculation of the maximum cutting possibilities or if it can still run in the perfect conditions. We set a tool life, and every time the tool life is nearing its end, it's being unloaded automatically out of the machining area back into the tool magazine, and then it's positioned in an unload station. The system tells the operator that there is a tool with end of lifetime available in its unload station, so he can perform his task in renewing the tool, etc. Of course, this does also mean that the process does not stop.
No. So there's already new tools in other chambers.
After Luk's machining steps, the parts go through an automated inline deburring and finishing robot. It adds flexibility to the process and keeps the finish consistent before inspection. Speaking of inspection, we'll join Kevin for the final steps of the process in quality control.
After about a working day of machining, the piece ends up here, inside the precision measuring room. So the idea is that this thing measures...
This thing indeed measures the machine part. So here we have the Renishow probe, which is mounted on our 3D CMM machine. And basically this probe is taking several points on the part. On this part, it's more than 1,000 points that it's taken. After the Renishow probe has probed the whole part. The computer is calculating all of the dimensions, all of the surfaces, all of the tolerances, and then it's being compared with the customer's drawing. Then we decide if the part is good or not.
It looks like it's done.
Yeah, it's done. Yeah, right now. It's done.
What happens with the part now?
The part goes back to our production facility. If it's good, if it's not good, it remains here.
Yep.
And then we need to check what is wrong with the part and so on.
And you can see if it's salvageable or whether it's
of course,
off to the melting pot again.
Yeah, indeed, correct. But if the part is good, which we assume that it is, it goes back to the production facility where it gets cleaned again. Mm-hmm. It gets packed in the packaging, and then it goes to our subcontractor, which is performing a nickel plating on the part. And then the part comes back here again. Mm-hmm. Then we do incoming inspection of the nickel plating and so on, and then the part gets an assembly here, and then it goes to the end customer.
Depending on the use case of the part, a different surface treatment will be required. This can range from very thin nickel plating to protect it against corrosion, to galvanized or other types of anodizing to give it a specific color or even paint. Depending on the treatment, IGW will send the part to a specialized partner.
So now Kevin is taking me to the very, very last stage of manufacturing.
Right now we are going to the final step of our production process, which is the assembly room, because some of our customers require that we do a pre-assembly. But let's go and check it out. Here we already see a part that is fully assembled, fully checked, and it's complying to the requirements of our customer. We already packed it. We put it in the crate. Now only thing that we need to do is close the crate, and it's off to our customer. So this first compartment we use for the incoming inspection of the parts. So the parts come from our subcontractor, and we check if the parts meet our requirements. If that is okay, then we are going to the second part of our assembly room, where the actual assembly is taking place. And here we can see our colleague Guy, who is basically assembling the part. He is putting more than 150 inserts in the part. Yeah, this is really important because we pre-machine the threaded holes, and afterwards we need to assemble an insert in it. Why? Because it strengthens the threads.
Yeah, because obviously aluminium isn't really...
Aluminum is quite soft, and therefore we need to put in an insert to strengthen the threads, so our end customer can assemble all of the components on the part.
All right.
So, and right now here, we see that Guy is assembling it. After the assembly, he cleans the part because he is assembling it with Loctite. You can see he cleans it with acetone because it dissolves the Loctite and it gets cleaned. He's also using fiber-free cloths. Also very important because we cannot have any lins, any fibers on
attached
the part.
On the part.
Yeah. And then after he's done with that, he takes the part into our darkroom. That's actually the final step of this part, where he checks the parts with UV light, because UV light lightens up the fibers, the dust, so we can see them and remove them.
Just to make sure it's a very clean darkroom. It's
very clean.
Unlike the one I imagined.
Every single day it gets checked and it gets cleaned.
And after successfully passing the inspection in the darkroom, the part is shipped off to the customer. If you have more questions about the production facilities at IGW, don't hesitate to contact the team. I'm sure they will be more than happy to help you out. I'm curious what part of future tech you will design and build together with IGW.